Whether you're using a simple dynamic routing protocol such as RIPng or a more complex routing protocol like OSPF, you will want to verify your configurations and the results you're receiving based on those configurations. There are a lot of show commands at our disposal. We have commands like show IPv6 RIP, which is going to display the process that's running, our timers, some general statistics about RIPng, as well as the interfaces that are participating in that RIPng process. We also have the show IPv6 RIP database command, which is one of my favorite commands, simply because we get to peer in and see what information we have learned from our neighbors, and it's also going to tell us whether those routes that we learned from the neighbors are being used, meaning have they been installed in the routing table or have they not been installed? And if they're not installed, why? Is it because there's a better source of routing information, meaning some other source has a better administrative distance than RIPng? It's quite possible. And lastly, we have the show IPv6 RIP next hop command, which allows us to verify who the next hop routers are. So essentially, based on the information I have learned from my neighbors and the next hops that are available, let's put that all together so you can see essentially who your neighbors are, even though you don't form neighbor adjacencies with RIPng. So let's go to the live environment and let's take a peek now on R1 at, first of all, the output of show IPv6 RIP. And as we can see here, the process name was router_RIP. The UDP port is port 521. We are using that multicast address of FF02:9 for our RIP routing updates. We're multicasting them out of our interfaces. The administrative distance is 120. So we can verify whether it's been modified or changed on this particular router. Maximum pass is 16. We can see how often we're going to send an update. Again, a value that can be changed. It's simply a timer. By default, it's 30 seconds. And routing entries are only going to be valid for 180 seconds, meaning that if I have not received an update in 180 seconds, that routing entry is now invalid. And then we're going to have to flush it out of our routing table. We can verify if split horizon is on or off, and by default, split horizon should be on. And it's one of those features that you really don't want to turn it off unless it's absolutely necessary. For example, maybe in a DMVPN environment, a multi-point interface like frame relay or with multi-point GRE. If you have routes coming in and you need to advertise them back out that exact same interface, then you'd have to shut off split horizon in those cases. We can see down below the interfaces that are participating in this process: gigabit 1/0.1 and gigabit 2/0. And lastly, if there is redistribution, we can verify whether redistribution is on or off, and particularly what protocol we are doing redistribution for. The other show command I want to take a look at is show IPv6 RIP database. As I said, this is one of my favorite commands for verifying our RIP routes that we have learned. And if you notice here, we have learned 2001 AA12:64. It's 2 hops away. This is the particular interface that we will use to reach that network. And it is using the next hop address of FE802. That's actually R2's address, link local address, on its gig 1/0.1 interface. Why would I be learning that from R2? Well, we enabled the routing process on the interface, and that is a local area network. R1 and R2 are connected to Ethernet switches on the same subnet. As a result, they will receive RIP updates from each other. But notice, it's not installed. It does not say installed. Whereas if you go a little further down, you'll see that this particular route is installed, this particular route is installed, and this one's installed. So why is it not installed in the routing table? Because there is another source of information for that exact same network. And what would that be? It would be directly connected. Directly connected has administrative distance of 0. Therefore, this RIP entry is not going to end up in the routing table because there's a directly connected route with a better administrative distance. Same thing here. This is a directly connected network as well. But because we enabled the RIP process on the interface, the network the interface belongs to, which are these networks we see here, get injected into the RIP database. So that way there we can tell our other neighbors about it through the process of sending RIP updates. And down below we can see our default route that we learned. And to reach that default route, gigabit 2/0 FE80:31. And lastly, the show IPv6 RIP next hops lets me see essentially who my neighboring routers are or who I've learned information from, just based on extracting the information out of that RIP database. As you can see, there's a lot of next hop addresses there in the RIP database, but what does it really break down to? Well, I really have only learned information from a router at FE80:2 and a router at FE80:31. So unlike EIG, RIP, and OSPF that actually form neighbor adjacencies and care about who their neighbors are, RIP kind of has an idea who its neighbors are, simply based on the next hop addresses, and you can double check who the next hops are and essentially who the neighbors are or who we've learned information from by taking a look at this show IPv6 RIP next hops command.